Hello, I'm Doug Eggert. I'm Director of Product Management at Tobii, working closely with our XR technology partners to integrate Tobii eye tracking into virtual and augmented reality headsets and smart glasses. These are exciting times for eye tracking as it becomes a core enabling technology for spatial computing. At Tobii, we're excited to join SIGGRAPH this year to present the recent progress that we have made exploring additional practical applications of Tobii Spotlight. Tobii Spotlight is the eye tracking technology that we have developed specifically for foveation-based optimizations to enable immersive and engaging user experiences. We'll start with a quick overview of the methodology behind Tobii Spotlight. The image here is intended to represent the full human field of view. Now let's look at the diagram on the right to describe how the eye captures this scene and transmits the information to the brain. Visual perception starts with the light passing through the lens and focusing it on the retina at the back of the eye. We see the fovea shown as a small depression. This is a pocket of densely packed photoreceptors that translate light into the biological signals which are transmitted through the optic nerve to the visual cortex where the information is processed. The result being that only a very small region of about 1 to 2 degrees of the entire 220-degree field of view are perceived by our visual system with clarity and distinct color. We see this degradation in the peripheral region represented with the blur and reduced color saturation in the image. We have developed Tobii Spotlight technology to leverage eye tracking in order to exploit these natural optical characteristics. By providing an accurate and low latency eye tracking stream developed specifically for foveation, system resources can be optimized to align display technology with how the human visual system works. As we see on the right, we can target specific regions of the images in the stereoscopic displays in order to focus computational resources on producing content, the best content, right where the user is looking. This type of optimization is key to enabling a level of visual clarity and performance in which the real world and virtual content becomes indistinguishable in spatial computing. Our proof of concept builds on a similar type of compression that is already being used in VR headsets today. This animation depicts this method of foveation, which we refer to as static foveation. It does not use eye movement specifically, but instead applies head movement to determine a large central region of the field of view in which to preserve the full resolution of the image. Compression of the image can then be applied to the smaller areas in the periphery. This is effective in the current generation of VR headsets with lenses that typically produce blurring in the periphery. The peripheral regions of the display can be rendered in lower resolution without being detectable by the user thanks to these imperfections in the optics. We introduce a method in which we can improve on static foveation while negating some of the potential trade-offs. With eye tracking, the user's gaze is known, and this makes it possible to zero in on a smaller region of interest in which to maintain full clarity in the images. This provides a much larger peripheral region in which compression can be applied without a perceivable degradation in visual quality for the end user. This application of eye tracking will be increasingly important in the next generation of VR headsets, with new lenses delivering improved optical clarity over a larger field of view of the display. With our findings, we are confident in the feasibility of Tobii Spotlight technology to address some of the key challenges facing XR. The proof of concept effectively simulated the low latency network demands and demonstrated how a foveated transport codec could effectively reduce bandwidth usage and minimize latency in the rendering pipeline. Eye tracking can be leveraged to meet the compression needs required to deliver high fidelity content while maintaining comfortable and immersive user experiences over a network. Finally, this concept demonstrates optimizations suited for the next generation of headsets facing the challenge of delivering ultra-realistic content for truly immersive VR experiences while maintaining the comfort, ease of use, and freedom of movement that a wireless headset can deliver. I will now hand it over to Dennis Rodell to explain the innovative work that Tobii has done to explore the potential of a foveated transport codec for virtual reality.
Thanks, Doug. My name is Dennis Rodell, and I am a software developer at Tobii working on foveation technologies. I will describe Tobii's foveation codec in more detail. Before I dive into the foveation codec, I first want to explain the concept of split rendering. Split rendering is a concept which offloads rendering and computation from the client to a dedicated PC or an edge server. In this image, we have a VR headset which sends sensor data, information such as headset position and rotation, controller input, and so on, to the server. The server uses this information to run application logic and render an image. The rendered image is then sent back to the client to be displayed. For example, this can enable an untethered Android VR headset to run a game with high fidelity graphics by offloading rendering to an edge server, which then transmits back the rendered images over network. In this diagram, we have the user with the VR headset in the left box and the server in the right box. In between, there is a network connection that they use to transfer data. To produce one image in this system, we start off by sending the headset pose from the client to the server. The server uses this pose to render an image, which it then feeds into a video encoder. The output from the video encoder is then sent back over the network to the client, where a video decoder decodes the data and produces an image. The image is then reprojected to fit the current headset pose and is then displayed to the user. This is a simplified flow of a split rendering system. It is in this system where we introduce the concept of a Foveation codec, with which we are aiming to decrease the time it takes for the system to perform the steps inside this outlined area. By introducing a codec which leverages information about where the user is looking, we aim to compress the image before it is passed to the video encoder, and by doing so, reduce the time spent encoding and decoding the image, as well as reducing the time it takes to transfer data from server to client. If we then introduce our Foveation codec into this system, we start off on the same point. The client sends the VR headset pose to the server, which renders an image. The client also sends gaze data, information about where the user is looking, to the server. Since the gaze information does not impact the rendering of the image, the server does not need this information until after rendering has finished. This is in comparison to foveated rendering, which uses the gaze information at the time of rendering. The server uses the gaze information to compress or warp the rendered image, thereby reducing its size before it is being sent to the video encoder. This allows the video encoder to process the image more quickly and also, in turn, produce a smaller output. The output from the encoder is, just as before, sent to the client and decoded. After the image has been decoded, it is being unwarped, meaning it's being restored to its original size. The image is then reprojected to the current headset pose before being displayed to the user. To summarize the Foveation codec, it performs a gaze-based image size reduction before video encoding. This has a few benefits. It decreases the latency for the video encoding and decoding. It also decreases the amount of data needing to be transferred, which reduces the bandwidth use and therefore transfer latency. It does this while maintaining quality where the user is looking in the VR headset. To show how this looks inside a headset, we created a video capture of a user wearing a VR headset while using the Foveation codec. The red box has been added to visualize where the user is looking. When the user looks around, we can see that the parts where the user is looking remain sharp, while other areas appear blurrier. If I then pause the video, we can break it down to the steps which I described previously. On the left, we have the image as rendered on the server, without any compression applied. That image is then compressed or warped, based on where the user is looking, to become the smaller image in the middle. If we zoom into the middle image, we can see that the region where the user is looking appears normal, while the edges appear warped. For example, the blue building on the right has its shape completely warped, and the brown building and skyline to the right of the blue building are barely visible. The Foveation codec compresses the part of the image which lie in the periphery of the user. If you recall what Doug explained earlier, we have high visual acuity in the fovea, which is roughly the size of your thumbnail when looking at it with your arm extended in front of you. Other parts of the eye have lower visual acuity, which is what we leverage when we perform this compression. The center warped image is the one which is being video encoded, transferred over network, and decoded by the client. The client then has the center image, and then has to reconstruct the image to its original size. Using the gaze information and the compressed image, the image can be reconstructed by essentially reversing the compression. The image on the right shows the final reconstructed image, which is displayed to the user. The parts of the image where the user is not looking appeared blurry, but the compression is designed in such a way as to mimic the physiological properties of the eye, meaning it shouldn't be noticeable to the user. Note here that not all of the image shown is necessarily visible for the user in the headset, due to the fact that the image you see has extra reprojection margins, which are not visible to the user always. These margins are being used to reproject the image to account for head movements which have occurred from the time when the image was rendered. The video was also recorded with a high compression in order to show off the effect. Looking at the video and the images from the last slide, the reconstructed image appeared blurry in the user's periphery. This is partly due to the Foveation codec's compression, but it's also due to additional filtering that is being applied to the resulting image. This filtering is applied on the client when reconstructing the image in order to ensure that the image doesn't exhibit artifacts which may be perceived by the user. If we zoom into a part of the image which lies in the peripheral region of the user, the image appears relatively smooth. By comparing the unfiltered image to the left and the filtered image to the right, we can see that the unfiltered image exhibits more sharp edges, which are being smoothed out by the filter. This is an important step in the codec, because even though the user will never see this in their fovea, the eye is very good at noticing contrast changes and movement in the periphery. And next, I will talk about how we evaluated the Foveation codec and the results from the evaluation. We wanted to evaluate the Foveation codec in a way which represented a realistic usage scenario. To evaluate the Foveation codec, we designed a study focused on user perception, which sought to find the limits, both in terms of compression and also at which latencies it could be used. If the Foveation codec is to be used in systems with networking, we want to know not only how much it can compress, but also with how much latency it could feasibly be used with. For the study, we decided to take the base architecture that I explained previously and replace the two-system setup to instead running everything on one system, which contains both server and client. We also removed the video encoding and decoding, and this was done to give a more controlled environment in which to run the experiment. We added a simulated latency, which simulates the latencies of the network transfer as well as the video codec. Since in a real system, there are network latencies also when transferring gaze data, we included this in the simulated latency. To get a sense of what latencies exist in split rendering systems, we looked at what existed in other projects and solutions. One example we found was an evaluation by NVIDIA for their Cloud XR system, where they tested running an HTC Vive headset over a local Wi-Fi system. In that example, they saw a difference of roughly 40 milliseconds when comparing to running a local system. This difference includes, among other things, the time to encode and decode the image, as well as network transfer. We used this as a baseline and set our simulated latency value slightly higher, going all the way up to 55 milliseconds, which equates to 5 frames in a 90 Hz headset. For the study, we created an experimental layout where a participant would be placed in a virtual scene while we employed different combinations of compression and simulated latency. Each participant was asked to look around and interact with the scene normally for 15 seconds, after which they were asked, "Did you see anything out of the ordinary?" The participant was asked to choose from one of the following alternatives: no artifacts visible but not annoying, or annoying artifacts observed. Participants were also asked to describe what type of visual artifacts they perceived, if any. Using this experiment, we could gather both quantitative as well as qualitative data. This experimental setup also allowed us to use randomized order of combinations in a double-blind fashion. We also designed the study in order to make every participant see a defined combination 2 times during the experiment to see if we noticed any inconsistencies in how the participant responded. We also included a control combination which used no compression and no latency in order to make sure that the participant didn't perceive artifacts when the codec was bypassed. For this study, we used 2 different types of VR headsets, the HTC Vive Pro Eye and the Tobii HTC Vive Dev Kit, which is an HTC Vive with retrofitted Tobii eye tracking. Both of these headsets have a display refresh rate of 90 Hz and an eye tracker frequency of 120 Hz. We wanted to perform the study using one type of headset, preferably with as high resolution as possible, but due to COVID-19, we were unable to perform tests in person and instead had to run the tests remotely, using whatever equipment participants had available. With the data from the study, we constructed a graph which plots compression ratio on the x-axis and simulated latency on the y-axis. Each point corresponds to one participant seeing one combination of these two. Green means that the participant said that they noticed no artifacts, yellow means they saw artifacts but they were not considered annoying, and red means that the participant observed annoying artifacts. In the bottom left is the control combination at 0 simulated latency and a 1:1 compression ratio. What we can see here is that at low latencies, high compression ratios were possible, but as latency increased, the compression ratio had to drop in order to not be considered annoying for participants. This is due to the Foveation codec requiring relatively low latencies as participants quickly look at different parts of the screen. The outlined area shows roughly the zone where the study finds the limits of the current Foveation codec from the perspective of user perception. As latency increases, users start noticing the effects of the codec before the system can produce a new image which matches where the user is looking. In summary, I have presented a Foveation codec which uses gaze-based image size reduction. Based on the study we performed, we believe that, depending on the latency of the system, pre-video encoding compression levels of up to 6:1 are feasible and can practically be implemented in current architectures in combination with conventional video codecs such as H.265. We also believe that as field of view and optics improve in VR headsets, this technology will see an increased utility. Lastly, I want to mention that we are working with our innovation partner NVIDIA to explore the potential of this technology. We welcome more partners to join us and use this technology to enable more possibilities in XR in the future. We are very excited to present this emergent technology, and we believe that it can deliver the compression needed to enable delivering high fidelity content for the next generation of VR headsets. If you're interested to hear more about this, feel free to contact us. If you want to learn more about other eye tracking use cases, you can scan the QR code on this slide. I'd also like to acknowledge the team from Tobii's side who has worked on creating the Foveation codec and its evaluation. Alexei Besugli, Richie Brannon, and Ralph Biedert. Thanks for watching and enjoy the rest of the conference.